Now, I didn't post yesterday's lecture recording. Some of you noticed that already. So those of you in lab today, just make sure you remind me, okay? Because it's already rendered and everything. It's just a matter of uploading it to YouTube. I usually do that during lab, and we didn't have lab yesterday, so it got me off schedule. Then my computer this morning was on 2%, kind of like my gas tank. Hence it's plugged in. Okay, all right, so let's get into naming. Are there any last minute questions about fluid structures? It's really important you get those down. Those will be covered very quickly in your next chemistry class. So make sure you got those down. Oh, okay, so let's go ahead and go on then to naming. Now, I passed out this handout here. This is the common ions that I run into. You're not going to need to memorize this. I'll give you this on the test. However, your next chemistry class, they may have you do a few of these, subsets. And it depends on the teacher, which ones and all that stuff. And you'll always have this or backup. Okay, let's talk about the way this is organized. As you remember, an ion can either be positively charged or negatively charged. Positively charged are called cations. There are two. Negative ions are called anions. Okay, so I've got the cations on the left, anions on the right. Now in chemistry, you always put the positive things first. So whenever we list an ionic compound, the cation is always going to go first, the naming. Anion goes second. It's kind of the way I like to lead my life. Positive first, right? Minimize the negative. Okay, now over here on the far right, I've labeled this covalent. So whenever we're naming covalent or molecular compounds, we're going to be using the mono, di, tri, etc. Ionic compounds, we are not. No exceptions. Okay, so molecular or covalent, we have to say how many of the atoms we have in there. With the ionic, there's another way we're going to be doing it. We don't have to say mono, tri, hepta, whatever. Okay, it'll make more sense in a minute here. Okay, now, ionic compounds always have a cation and an anion. Always. Sometimes teachers or books will refer to them as a metal plus a nonmetal. I remember from the periodic table, the periodic table has the nonmetals in the top right, and most of the table are metals. A molecular compound is something else. It could be two anions, two cations, but it's never one of each. Then it becomes ionic. So whenever you're naming, the first step is to determine whether it's covalent or ionic. Now, you check for ionic first. So let's look at some examples. Sodium chloride. Sodium chloride, common table salt. And I want to emphasize in chemistry, when we say salt, that is not sodium chloride necessarily. There are literally millions of salts out there. And only one of them is sodium chloride. You could have calcium chloride, you could have potassium chloride, potassium nitrate, all those are salts. What is a salt? cation plus an anion. Very, very generic definition. Okay, so we have to determine whether sodium chloride is an ionic compound. So what you do is you look on the left side of your common ion chart. Is sodium listed there? Yeah, it is. Towards the bottom, down here. Okay, so cation, and what about chloride? Is it on the right? Okay, so it fulfills the definition of ionic. So now we use the ionic naming convention, which is not the same as the covalent convention. That's why we have to know which one you're dealing with. Okay, let's look at another example. Here we have chloride iodine, CLI. Is this ionic or molecular? Okay, this has to be positive. This has to be negative for it to be ionic. Just like the sodium was positive, chlorine was negative. Now, if we look, Cl and I, they're both on the right side. They're both anions. So that means that's, bless you. So that means that's covalent. Okay? And we could also have something like this. Na, sodium, we know is a cation, and so is potassium. So that is molecular or covalent as well. Even though there are ions there, it's got to have cation and an anion. Now, I already mentioned yesterday what a covalent bond is. Covalent bond is for sharing valence electron. Ionic bond means we're transferring electrons. So an ionic bond, one or more electrons are transferred. Here, electrons are shared, like when we're doing Lewis structures. Now, you can also do ionic structures. You can do Lewis structures of that as well. So that on your last page of your dry lab, you're going to be doing some ions. And all you're doing there is figuring out where the ion has come from, which makes it a plus, or is added, which makes it negative. And there's only two problems there. So, okay, so ionic means electrons are transferred. That's why one is positive and one is negative. The positive one gives up electrons, the negative one receives it. You always have to have a donor and a recipient. Always. You can't have stray electrons. That's called beta radiation. Beta radiation is bad. Okay. All right, so let's go over the covalent naming system first. Now, both these conventions have two parts. Now, we're doing covalent now, or molecular. Okay, over here is the, oops, let's not do that. First part comes from the periodic table. So let's take sodium chloride again. Okay, on your periodic table, you find Na or that list of elements, alphabetical list I gave you. Either one. It's better to use the periodic table so you get an idea where everything is located. But you can use the other list as well. Okay, so on the periodic table, Na says sodium. Over here, you have to have the ion with an "ide" on it. So if you look on the common ion chart on the right side at the top, you'll find it's not chlorine, it's chloride. Now, with see, this is an ionic. Let's do ionic since I've started with this. Okay, now, remember I said with ionic, we're not using the mono, di, tri, etc. We have to balance the number of ions by their charge. Because ionic means it's charged. Okay, so what's the charge with sodium? Look on the left side. +1. What's the charge on the chloride, the right side? -1. We have to have a net 0 on the charge. So what charge do we have net? 0. +1, -1, totally cancels out. So let's do another one. Let's do sodium carbonate. Okay, Na we already know is sodium from the periodic table, and it's got a +1 charge. Carbonate, find carbonate on the right side. What's its charge? -2. What is the net charge now? No, 2. Wait. What's the net charge now? Not 0, is it? So we have to make it 0. How are we going to make it 0? We need to up the positive charge, right? We do that by adding a subscript. So the formula for sodium carbonate is Na2CO3. And we need 2 sodiums to balance off the -1 charge of the carbonate. Now this has to always happen with ionic. You have to have charge balance. Now with molecular covalent, there are no charges. So there's no way to balance it via charge like you know with the ionic. About aluminum sulfate. Okay, what's the charge on aluminum? What is it? +3. What's the charge on sulfate? -2. So is this net zero? We gotta fix it then. How are we gonna do it? If I was to add 1/2 plus 1/3, is that equal to 2/5? No. Please, all of you say no. What do we have to do? Common denominator in this case is, which is what? 6. So we change the 1/2 to 3/6, the 1/3 to 2/6. Everything ends up being 5/6 is the answer. Okay, so we're kind of got the same situation here. We have a 3 and a 2. We have to balance those. So what's the common denominator between 3 and 2 again? It's 6. So how many 3s are in 6? 2. How many 2s are in 6? 3. Now we have +6, -6, and that's 0. Okay? So whenever you see this 2, 3 bit, and we're going to run into this when we start balancing equations as well. So whenever you see 2s and 3s, you're having to match them up. Think of common denominator. Think of 6, because it'll come up. Nothing else will come up more complicated than that. It'll mainly be 2s and 3s. So just keep in mind 6. Okay? All right. So notice on the bottom here, I don't say dialuminum sulfate because it's a cation. We already know the charge on it. Same with the sulfate. I don't say disulfate or trisulfate. Now, when we get to covalent, we are going to have to say that because they aren't charged, and there's no way to tell how many of each. We have to tell it how many of each. Now, in this unit, you have to go back and forth between the name, the formula to the name. Okay? On your test, you're going to have both examples. So you're going to have 4 different things to deal with naming-wise on the test. I'm going to give you a ionic formula. I want you to name it. I'm going to give you a formula, and then you need to name it. Same with the molecular or covalent. Now, there's a lot of little nuances with this ionic naming. And this school is unique, and I don't know why they do it this way, but I don't do it in my class. Okay, if you look at some of this stuff, let's look at iron. Now, in the food industry and the ag industry, they use the right-hand name for this stuff, which is the old name. And frequently the biochemistry group and biology groups also use the old name. In chemistry and physics, they use the new, when I say new name, and I'm talking 80 years ago, it's not exactly new anymore. It's even older than me, by much so. It says iron 2, iron 3. So this is the deal. Roman numeral stands for the charge. The old name is ferrous, and there's no way to tell from the name ferrous what the charge is. That's why they switched over to this newer version with the Roman numerals. Iron 3 is going to be iron plus 3, and the old name is called ferric. Like, for example, rust is ferric oxide. No one calls it iron 3 oxide. We call it ferric oxide. So keep that in mind when you see these names. For example, if I said write out ferrous chloride, what would that formula be? Ferrous is +2, chloride is -1, so we need FeCl2. Cl is -1, we need two of them, balance the +2 in the iron. Another weird thing is hydrogen. There are two forms of hydrogen. Hydrogen has one electron, and it's an anomaly of all the elements. Because it has one electron, one proton, no neutrons. It's the simplest of the elements, also the most prolific in the universe because it's so simple. So allegedly during the Big Bang theory, it was the easiest to produce. That's why there's so much of it. And then it starts combining with other things and being blown up and forming all kinds of stuff. But basically, it's the simplest element. Because of that, it's in two forms. It's an anion and a cation both. It's a cation when it's with an acid. That you're going to see when we get into the acids unit. An acid is defined as disassociating an H. And that disassociated H has got a positive charge. Normally, it's negatively charged. So if you see on your chart over here, on the right side, the very top, it's called hydride, H-. So it's kind of weird. It's kind of both. So most of the time it's hydride. For example, we were to write aluminum hydride. Aluminum hydride. Okay, aluminum's +3. Hydride's -1. So that's ionic. So the formula for that's going to be AlH3. So until we get to acids and bases, H is going to be negative. And it's going to be called hydride. Yeah.
Remember where it's like two aluminum and 6 hydrogen?
Mm-hmm.
So how do you figure out when it's instead of this line?
And you need to know the definition of an acid. Let me show you an example where acetic acid. H is all over the place, right? Acetic acid, definition of an acid is, will it disassociate an H plus? If it does, it's considered an acid. So what happens is, when this disassociates, it becomes this. Notice, not all the H's come off, only certain ones. And why would you guess that's so? What rules the universe? Stability, exactly. When an H comes off that's not in a certain location, it's very unstable, so it doesn't happen. This H coming off, this is called acetate, very stable. What happens if, because it's stable, it happens. If one of these comes off, you're going to end up with this is very unstable, so it doesn't happen. So, and the opposite of an acid is a base. That's when OH comes off, is a negative. Don't worry about writing that down because we're going to get into that in intimate detail when we talk about acids and bases. So, so to answer your question, I think I'm going to answer your question. So you can have both hydrogens there, but they aren't that same hydrogen. One can come off easily, the others absolutely cannot come off. Because it's a stability question. It's always stability. If in doubt, because it's less stable or more stable. If in doubt. It's a great answer. And there are two deals to that. There's something called entropy, which is the degree of randomness, and enthalpy, which is the degree of potential energy in that two states. And that's called thermodynamics. Okay, so anyway, that's an example of what you're asking. Now, was that your question?
It was like, why couldn't it be aluminum to hydrogen 6?
It could be that.
Like doing it.
Normally, you go to the simplest,
Oh, because it's
yeah. So, in that situation, Al2H6, that's called a dimer, D-I-M-E-R. Di means two. Weak acids do that all the time. For example, acetic acid forms a dimer. But the formula still remains CH3COOH. But it ends up being physically a dimer. Has anyone here had a D-dimer test? Curiously, you're all young. When you get old, did you study that, Aaron, for EMT? It has to do with blood clotting. When you have a blood clot and the clot dissolves, it produces this protein. And the test is checking for the protein presence. And if it's there, that means you had a blood clot. Whether it's still there or not, that's what they have to check out. My daughter's going through that now. She got a D-dimer test and it was higher than normal, meaning she had a blood clot somewhere. And then checking now if it still exists or not. Okay, so dimers used a lot in chemistry. Okay, let's see here. All right, so the ionic naming and formulas, you just have to practice it a lot. That's what's nice about the dry labs. Okay, so let's go into that other convention, the molecular one. So let's look at N2O3. All right. Is that ionic or covalent? Well, look at nitrogen. Is that a cation or an anion? An anion. And what about oxygen? It's also an anion. Okay, so now we have to use the covalent naming or the molecular naming system. So we're going to have two parts again. Remember, this is an ide over here, and this is from the periodic table. Okay, so we're going to go nitrogen, oxide. There's no charge. This is not ionic. So we have to tell it in the name how many of each. So we have two nitrogens, that's di. Top right says the numbers. And we've got three oxides. So that's tri. So it's dinitrogen trioxide. Most people find the covalent or molecular formula names easier than ionic. Some people do. Some people say they're about the same. Okay, so I'm going to repeat this. Always name for covalent and molecular how many. With ionic, you never mention how many because the charges dictate how many. Yeah.
Nitrogen appear as nitride.
Yeah, it's on your chart.
Yeah, I was looking for nitrogen, not nitride.
Ah. Yeah, so you have to have an "ide" on the second part of the molecular or covalent naming. And those are on the top right of your common ion chart as well. Okay, does that make sense? So if you saw this dinitrogen oxide, dinitrogen dies to tries 3 oxide. Again, you need to go back and forth. Now, there's one optional part on the covalent, and it's option. And your teacher in your next chemistry class may not call it optional, but I've seen it in textbooks a lot where it's optional. Okay, let's take this NH5. I've already determined that both of them are anions, so it's going to be covalent. So we're going to have nitrogen, hydride. We have one nitrogen, so that's mono, and penta are 5. So it's mono nitrogen pentahydride. This is the part that's optional. For example, water. Water is molecular, so it's going to be dihydrogen. Side. Yeah.
Determines which type of atom comes first. Why isn't it monoxide?
Um,
Or does it really matter?
it matters. That's a good question, actually. What would be a good answer? I've never been asked that before. Been asked about the ionic, then the cation always comes first. Theoretically, it shouldn't matter, but you never see OH2. Never see H2O.
But for less common, obviously H2O, we all know that.
But I know, but your argument still stands for H2O though. I don't know why the hydrogen comes first. That's something I'll have to look up.
So, but if we were to, in the lab or whatever, can we put it in any order if we don't know what it should?
If you see the formula though, just follow the formula. And the formula, if it's first, do first in the name. Like water. Okay, now the difference between these two, notice the mono over here on the right versus the mono on here is on the left. If it's on the left, it's optional. So the other way to write this would be nitrogen pentahydride. I tell my students to be consistent and don't have to worry about, is this optional? just put the mono in the beginning as well. I'm not gonna work it wrong if you do it, if you leave it off. The second mono on the right is not optional. You have to put it in. And that's the only real optional thing you can do with covalent naming, is this mono in the beginning. Okay, so that's kind of it for then it's a matter of lots of practice. Now you're gonna find sometimes the ion is not on the common ion chart. These are common ions, not all the ions. So look first here. It's not here, then look at the formula. For example, if I or go on. Um, there's a reason why, like iron is in two forms. Actually, it's in about 6 or 7 forms. These two are the most common. The reason why it's in 6 or 7 forms is because the ions, some ions are very unstable, some are very stable. Like if we look at silver, notice silver has just one ion, Ag plus. But it can just as easily exist as Ag plus 2, plus 3, plus 4. It's because the Ag plus 1 is very, very stable. The others are doable, but not all that stable. So the uncommon ones are not on this list. Most metals can form multiple charges. So if you see something like this, and you'll see this on your dry lab, actually. That correct. Look at the charge on sulfate, which is -2. So that means this collectively is -6. What must the one vanadium be? +6. You look on your chart at the bottom, on the bottom left. Does V6 exist? Does not. So it's an uncommon ion. So if you were to write this, it's going to be vanadium six sulfate. This Roman numeral 6 indicates it's a +6 charge. So if it's not on the common ion chart, look at what's going on. We know that sulfate is a -2. It's only exists as -2, period. The anions are much more stable than the cations. Those are kind of all over the place. And the common ones I've listed here, but they're still all over the place. So, and vanadium +6 means it lost 6 electrons, which is a lot to lose. That's why it's not very common. Okay, does this make sense? The sulfate is always -2, but automatically forces the vanadium, the one vanadium, to balance it off. That means it's got to be a +6, balance it out. Okay. All right. Now, I've gone over most of the gotchas on this. It's just a matter of practicing these. For example, on this one here. You see this formula. Parentheses are for ions that are multiple, like SO4 instead of just plain old S. So what it does is it groups them together. They're called polyatomics, ions. All those ions in the middle here are polyatomics. So whenever you see polyatomic ion, think parentheses to group it. If there's just, no, it's just, my dog last night, one of my dogs sleeps right here. And when she feels lonely, she wants to lick me. Usually it happens around 3 o'clock in the morning. And she's a little dog. She only weighs 7 pounds. So she's got a little bitty tongue. That's, and she was licking my nose last night. Driving me crazy. Okay. Notice here, we've got, if this is just a formula, and I asked you to write that. Okay, look over on the right side and find phosphate. Phosphate is a -3. That forces the iron to be a +3 to balance it out. Because there's one iron to take up all that negative charge. So the way you write it is iron 3 phosphate. Or ferric phosphate. So play those off each other, especially when you're looking at a cation that can have multiple charges. And you ask yourself, well, which one is it? Look at the anion, because the anions don't come with multiple charges. There's only one of them. So use the anion to determine what the positive has to be. What if we had that? And we don't know this guy.
Add another phosphate.
Problem with phosphate is -3. And you have 2 irons to balance it off. Anyone see a problem with that?
What? One iron has to have +2, the other +1, or one has to have be neutral.
Yeah, it's a problem. So some of these are not doable because you gotta have fractional numbers. Fractional numbers. Remember, that was Dalton. Dalton said you can't have, it's always in whole number ratios. Okay, so that's kind of it on nomenclature. Now, it is extremely important that you know this stuff. This is one of the weak spots going into 1A and 2A, nomenclature. So that's one of the things they want me to really emphasize. The other is Unit 1, problem solving, nomenclature. Big deal. Now, Unit 2 is going to cover nomenclature. And it's also going to cover some other things we're going to get into tomorrow and Thursday and next week. Those unit 2 and unit 3 are the horrendously important units in this class. Unit 4 is kind of what's left over. I'm not gonna call it fluff, but it's not a weak point going into 1A, 2A. All right, what are we looking at here? Are there any questions about this? Yeah,
For N2 open or would it be, disulfide, tetroxide
say it again.
or N2O4? Would be disulfide tetroxide.
Is this it? What you're talking
Yeah.
about? There's no sulfate there.
Oh, sorry, oxide.
So it'd be dinitrogen. Tetra, as you were saying, oxides. So that's what I had to do today for nomenclature. If you would like to stick around, we can practice Lewis dot structures as well. If not, we're gonna go to lab. So does anyone want me to do some more Lewis dot structures? Or? Hmm? Yeah. That means we're gonna do them. Okay, so let's go ahead and leave. I'm gonna end this video though.